Welcome to ASCP Preparation Camp. Today, we're diving into a small but mighty part of your endocrine system, the pituitary gland. It's often called the master gland, but the truth is, it's more like the translator-in-chief. It sits at the crossroads between your brain and your body, taking complex neural signals and converting them into clear hormonal commands that keep your body in balance. Before we get into the science, let's take a quick trip back in time. Believe it or not, the word pituitary comes from Latin and Greek roots meaning, to spit mucus. Why? Ancient thinkers believed the pituitary produced nasal secretions. Definitely not its proudest legacy, but hey, they were onto something else. They figured out early that the brain controlled the pituitary, which is spot on. Just not mucus, but hormones. Powerful ones. Modern science confirms this. The hypothalamus sends signals to the pituitary, and the pituitary releases hormones that regulate major glands, like the thyroid, adrenals, and gonads. That's why it earned its title, master gland. Without it, growth halts, metabolism falters, reproduction, stress response, and water balance, all disrupted. You might also hear it called the hypophysis, which translates to undergrowth in Greek. It fits. The pituitary physically sits just below the hypothalamus, nestled in a little bony seat at the base of your brain. So, what exactly does this tiny gland do? The pituitary doesn't just act like a boss barking orders. It's more like a skilled interpreter, taking neural inputs from the brain and translating them into chemical messages the rest of the body can understand. And how does it pull that off? Well, the pituitary works through some brilliant biological strategies. Feedback loops, especially negative feedback, that help maintain hormonal balance. Pulsatile secretion, hormones are released in rhythmic bursts, not constant drips. Diurnal rhythms, hormone levels that rise and fall with the time of day. And it adapts to the environment. Things like stress, light, and illness can all affect hormone output. This built-in flexibility is what keeps your endocrine system so responsive. But it's also what makes diagnosing pituitary disorders tricky, because hormone levels naturally fluctuate. A single lab result may not tell the whole story. Now, let's look at how it's built. The pituitary has three main parts, and each plays a unique role. Anterior pituitary, also called the adenohypophysis. It's the biggest section and does most of the hormone production we talk about. Intermediate lobe, the pars intermedia. In humans, this part doesn't do much. Occasionally, it forms small cysts, but they're usually harmless. Posterior pituitary, or neurohypophysis. It doesn't make hormones itself. Instead, it stores and releases two key hormones made in the hypothalamus, oxytocin and vasopressin, also known as ADH. And developmentally, these parts come from very different origins. The anterior pituitary grows out of a structure called Rathke's pouch, which is an upward growth from the embryonic mouth. Meanwhile, the posterior pituitary develops from the brain, specifically, the diencephalon. Wild, right? One part comes from the mouth, the other from the brain. That explains why their structures and functions are so different. As the pituitary forms, the median eminence and pituitary stalk connected to the hypothalamus, creating what's known as the hypothalamic-hypophyseal unit. And this system kicks into action early. Pituitary activity begins as early as 7 to 9 weeks into gestation. Now, let's zoom in a bit further. Within the anterior pituitary, there's a whole team of specialized cell types, each responsible for producing a different hormone. Lactotrophs secrete prolactin. Somatotrophs secrete growth hormone, GH. Thyrotrophs secrete thyroid-stimulating hormone, TSH. Corticotrophs produce ACTH, which targets the adrenal cortex. Gonadotrophs produce LH and FSH for reproductive function. Think of it as a hormone assembly line, with each team focused on its own specialty. As for where it lives, the pituitary sits tucked inside a bony cradle called the sella turcica, literally, Turkish saddle, at the base of the skull. It's surrounded by a protective layer of dura mater, and a little roof, called the diaphragma celli separates it from the hypothalamus above. The pituitary stalk, or infundibulum, pierces through this roof, linking the gland directly to the brain. That's where the real communication happens. The posterior pituitary receives direct nerve connections from two hypothalamic regions, the supraoptic and paraventricular nuclei. These nerves carry oxytocin and vasopressin straight down the stalk for storage and release. But the anterior pituitary doesn't get nerves, it gets blood signals. Specifically, through a unique circulation system called the hypothalamic-hypophyseal portal system. Here's how it works. The hypothalamus releases hormones into a set of capillaries in an area called the median eminence. These capillaries lack a blood-brain barrier, which makes it easy for hormones to pass into the blood. Long portal veins carry this hormone-rich blood down the stalk to the anterior pituitary, where they stimulate or inhibit hormone production. It's like a private hormone express lane, straight from the brain to the pituitary. Now that we've covered the pituitary structure and setup, let's get into how it actually works. At the top of the chain is the hypothalamus, your brain's hormonal command center. It's constantly receiving inputs, sensory, emotional, physiological, and it processes all that data through specialized nuclei. From there, it sends out hormonal messages, many of which go directly to the anterior pituitary. These signals aren't random. They follow a highly organized system of feedback loops, pulses, and biological rhythms. Feedback loops, the body's thermostat. Let's start with negative feedback, the classic regulatory mechanism. Here's how it works. The hypothalamus releases a hormone. That hormone stimulates the pituitary, which then releases another hormone. That second hormone travels to a target gland, like the thyroid or adrenal cortex, triggering hormone production there. Once enough of that end product hormone is circulating, it feeds back to the hypothalamus and pituitary to slow things down. It's like a thermostat in your house. When the room gets too cold, the heat kicks on. When it's warm enough, it shuts off. But the pituitary's thermostat is even more adaptable. Its set point can shift depending on stress, infection, or medications. That's why we call it an open-loop negative feedback system. Real-life example, the thyroid axis. Let's walk through a classic feedback loop, the HPT axis. The hypothalamus releases TRH, thyrotrophin-releasing hormone. This stimulates the anterior pituitary to release TSH, thyroid-stimulating hormone. TSH travels to the thyroid gland, prompting it to produce thyroxine, T4. As T4 levels rise, they feed back to suppress TRH at the hypothalamus, long loop. Suppress TSH at the pituitary, short loop. And in some systems, there's even ultra-short feedback, where the pituitary modulates its own hormone release. But here's the twist, in times of illness or high stress, glucocorticoids and cytokines can suppress this axis. Thyroid hormone levels drop, even though the gland itself is fine. That's the open-loop part in action. Flexible, adaptive, context-aware. Pulsatile hormone secretion. The pituitary doesn't just leak hormones all day long. It sends them out in pulses, short bursts that follow a rhythm. Each hormone has its own frequency and amplitude pattern, regulated by the hypothalamus. Take LH in men, for example. It pulses about every 55 minutes, with each pulse lasting 40 minutes or so. Change the frequency of GnRH pulses coming from the hypothalamus, and you change the LH release pattern. Faster pulses equals smaller LH output. Slower pulses equals larger LH bursts. Why pulses? Because if hormone levels were constant, target tissues might stop responding. The pulses help maintain sensitivity and efficiency. Circadian and diurnal rhythms. Some pituitary hormones follow daily cycles, called circadian or diurnal rhythms. These rhythms are often synced to environmental cues like light and dark, also known as Zeitgebers, meaning time givers. For instance, ACTH peaks early in the morning, around 6 to 9 a.m., to get you energized for the day. TSH peaks at night, with higher pulse amplitude, not frequency. So if you check someone's hormone levels at the wrong time of day, you might get misleading results. That's why endocrinologists pay close attention to when hormones are tested. Timing matters. We've talked about how the hypothalamus and pituitary communicate, but now let's meet the key messengers, the hormones themselves. First up, hypophysiotropic hormones. These are the signals produced by the hypothalamus that control the anterior pituitary. Most of them are peptides, though a few are bioactive amines, and they don't just stick to one target. Some influence multiple hormones. Major hypothalamic hormones. TRH, thyrotrophin-releasing hormone, stimulates both TSH and prolactin. GnRH, gonadotropin-releasing hormone, stimulates LH and FSH. CRH, corticotropin-releasing hormone, the primary trigger for ACTH. Somatostatin, inhibits GH and TSH, a dual suppressor. Vasopressin, ADH. While it's mainly known for water balance, it can also stimulate ACTH, especially during stress. And while these hormones are made in the hypothalamus, interestingly, you'll also find them in other organs, like the gut, pancreas, or other endocrine tissues. Their roles there are still being explored, possibly involved in local signaling. Anterior pituitary hormones, two main categories. The anterior pituitary makes larger, more complex hormones than the hypothalamus, and they fall into two big buckets. 1. tropic hormones. These target other endocrine glands, telling them to secrete hormones. Think of them as middle managers. LH tells the testes to make testosterone, or triggers ovulation in women. FSH supports egg development or sperm production. TSH directs the thyroid to release T3 and T4. ACTH stimulates the adrenal cortex to make cortisol. 2. Direct effector hormones. These act directly on tissues, no middleman involved. The two main ones. Growth hormone, GH, drives metabolism and stimulates the liver to produce IGF-1, which promotes growth. Prolactin stimulates milk production in the breast, especially important during postpartum lactation. Together, these hormones form a finely tuned symphony, one that can quickly spiral out of balance if just one note is off. Let's talk about something that surprises a lot of people: pituitary tumors. Sounds scary, right? But here's the twist. Up to 20% of people have tiny, asymptomatic pituitary tumors, discovered only after death. And even when we do brain MRIs, about 10 to 30% of people show some kind of pituitary abnormality, most of them totally harmless. So yes, pituitary tumors are common, but most are benign, slow-growing, and don't cause any problems at all. Still, it's important to recognize the types that do affect function. Types of pituitary tumors. Prolactinomas. The most common functional tumor. Produces excess prolactin. Often causes menstrual irregularities, infertility, or milk production outside pregnancy. Null cell tumors. Non-secreting. Cause issues due to size, not hormone production, like vision problems or headaches. GH-secreting tumors. Lead to acromegaly or gigantism. ACTH-secreting tumors. Cause Cushing's disease. TSH or gonadotropin-secreting tumors. Rare, but they do happen. Atypical tumors. What makes them different? Some tumors are classified as atypical, not because they're malignant, but because they grow faster, invade nearby areas like the cavernous sinus, show signs of aggressiveness under the microscope, high MIB-1 index, cell proliferation marker, increased p53 activity, more mitotic figures, active cell division. Interestingly, many of these stain positive for GH or ACTH, even if the person doesn't have obvious symptoms of hormone excess. Physiological enlargement. Not all growths are pathologic. The pituitary naturally enlarges during certain life stages. Puberty, as hormone demands increase. Pregnancy, especially due to lactotroph hyperplasia, prepping for milk production. Also, when a target gland fails, the pituitary often tries to compensate. For example, in chronic hypothyroidism, the thyrotrophs may enlarge. In gonadal failure, the gonadotrophs may grow in response. These are adaptive, non-tumorous changes, part of how the endocrine system tries to maintain balance.